On side talk in this session. It's my pleasure to introduce Cécile Huneau from the École Polytechnique. Cécile completed her PhD at the École Normale Supérieure in 2014 under the supervision of Jérémy Cheftel. She was then a research associate in Cambridge and held a lectureship in Grenoble before accepting a professorship at the École Polytechnique. And today she will speak to us about the high-frequency limit for the Einstein equations with U1 symmetry. Please.
So first of all, I would like to thank the organizer for the invitation to speak in this conference. So the work I will present today is a joint work with Jonathan Luke from Stanford University. And it's about high-frequency limit for Einstein equation in U1 symmetry. So, oops, sorry. So I think you have all the context this morning, but nonetheless, let me remind you what are Einstein equations. So in general relativity, space-time is described by a manifold M, which is most of the time a four-dimensional manifold, equipped with a Lorentzian metric, G. And the Einstein equation can be written Ricci minus 1/2 of R G mu nu equal T mu nu. So R mu nu is a Ricci tensor. You can see it as a second-order nonlinear operator for the metric. So that very roughly speaking, you can write it as G times 2 derivative of G times dg times dg. R is the trace of the Ricci tensor, is a scalar curvature, and T is the energy impulsion tensor. Its form depends on the matter model we are studying. So for instance, in vacuum, then the energy impulsion tensor is 0, and the Einstein equation in vacuum are in fact equivalent to the equation Ricci equal to 0. An example of solution is given by Minkowski spacetime, which is the metric M equal minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. But it's not at all the only solution of Einstein vacuum equation. The set of solution is dynamical. But for the purpose of the talk, let's see another maybe less known example of exact solution of Einstein vacuum equation, which are plane wave solution. So we can consider a metric of the form minus du dv plus b of u squared e to the omega u dx squared plus e to the minus omega of u dy squared. So this metric is the metric coefficient depend only on the variable u. They do not depend on v, x, and y. U and v, you can see them, if you want, as isotropic coordinates, like t plus z and t minus z. And so if you want it to be a solution to Einstein vacuum equation, then you can choose the parameter omega as you want. It's a free parameter. And the Einstein equation are equivalent to a second-order ODE for b, which is 2 derivative of b plus omega prime squared times b equal to 0. So now, once we have this kind of solution, we can, since omega is free, we can choose omega to be something which depends on a parameter lambda, which will be lambda alpha of u times cosine of u over lambda. So alpha is just the amplitude. And so now I note G lambda the corresponding metric. So I want it to be a solution to Einstein equation. So B lambda should satisfy the second order equation there. And now we can ask what happens if we let the parameter lambda tends to 0. So letting lambda tends to 0 means taking the high frequency limit. So if lambda tends to 0, then omega lambda, which has a factor lambda in front, is very difficult, in fact, to point. Omega lambda will tend to 0. But in the equation for B, there is a omega lambda prime squared, and in fact, omega lambda prime squared do not tend to 0. In fact, it tends to 1/2 of alpha of u. And so if we take lambda to 0, then the metric G lambda will tend to a metric which is the same, but with omega is equal to 0, and B is some B0, which now satisfies the second order equation, B0 second plus 1/2 of alpha of u squared B of u equal to 0. And you can compute the Ritchie tensor of this metric G0, and it happens that it's not 0, because B0 do not satisfy the right equation for it to be a solution to Einstein equation. So, in fact, the Ritchie tensor of G0 is this alpha of u squared d mu u, and this is not random right-hand side. It corresponds to the energy impulsion tensor of a null dust. A null dust is a fluid without pressure and isotropic. Okay, so this is just an example, but more generally, one can ask what happens if we consider a sequence or a one-parameter family of solution to Ritchie equals 0, such that the metric G lambda converges to G0 uniformly, where G0 is a smooth Lorentzian metric, and such that the derivative of G lambda are bounded in L2. So, for such a sequence, one can compute may compute the Einstein tensor of G0 and call what appears in the right-hand side the effective energy impulsion tensor. And the question that will interest us is what can appear at the limit. So let me give you some motivation on the history on the problem. So the first one who studied this problem was Isaacson, who was a physicist, in 1968. So he studied gravitational radiation in the limit of high frequency. So almost in the same time, Choquet-Bruat also gives the same kind of construction in a more with a more mathematical point of view, but it was still a formal computation of solution, high-frequency solution of Einstein equation. So the paper is in French, so it's why I've written the title in French. And then Burnett in 1989, studied still the same problem and give a conjecture that I will describe in the next slide, so I keep it for now. Then the problem was quite forgotten until Green and Wold studied it again in cosmology. In fact, they wanted, so in cosmology, the universe is assumed to be isotropic and homogeneous, but homogeneity is not true at small scale, and what they wanted to know is what are the effects of small scale inhomogeneities in the large scale, and they propose a framework to study this perturbation, which was the framework of Burnett. So then there have been a lot of papers because this framework, in fact, was quite controversial for the physics community, but I don't quote them. So then with Jonathan Luck, we wanted to do something more general in this problem, but we stick with still some restriction, which is U symmetry. So I will speak about this in the following of the talk, so you will see. And then there have been some more recent work by Luck and Roniansky, where they study also this problem, but in the context where there is angularly regular solution to Einstein equation. And very, very recently, in July, there has been also some work by Gerard and Teixeira da Costa on Burnett conjecture that I will present now. Okay. So what is Burnett conjecture? So you consider a sequence, the same setting as I presented before, a sequence of solution to Ricci equals 0, which converges in this way. G lambda converges to G0, smooth Lorentzian metric, and G lambda is bounded in L2. Then the Burnett conjecture that the effective energy impulsion tensor should be the energy impulsion tensor of a massless Vlasov field. So what is a massless Vlasov field? It is described by a density of particles in position and frequency, f of xp. And the energy impulsion tensor is the integral over the mass shell. The mass shell is a set of p in the cotangent space, which are isotropic. And so the energy impulsion tensor is the integral over the mass shell of f times p mu times the measure of the mass shell. And this density of particles should be transported along geodesic, and this can be written as an equation, a partial differential equation with respect to the variable x and p. Well, here it's it's pi, not xci, which is this one. So the assumptions which are made for Burnett conjecture, in fact, is like in many conjecture, finding the right assumption is part of the problem. It's not at all clear that these are the right assumption to make to obtain the result. We don't know yet. Okay. So let me give you some idea of what can happen in general. Why is this effective energy impulsion tensor appearing? So if with our always the same hypothesis, we have that the derivative of G lambda should converge weakly to the derivative of G0, because because G lambda, we assume that G lambda converges to G0 strongly, where G0 is a smooth Lorentzian metric. So if we have weak convergence of derivative, this does not imply that the product of term of the form dg lambda times dg lambda should converge also, even weakly, to the product of the same derivative of G0. It's what we saw with the example of plane waves. And in Einstein equation, with the rough form I showed you at the beginning, there are plenty of terms which are of the form derivative of G times derivative of G. And so this term lead to defects. And so the usual defects which can appear may be due to concentration. So for instance, if you consider a sequence UN, which is nd times some cutoff function of n times x minus x0, and if you let n tends to infinity, then un converges weakly to 0, but un squared converges weakly to, not to 0, but to the Dirac measure x0. So the limit up there, if our sequence is bounded in L2, it means that the product is bounded in L1, so up to extraction, it may converge to it should converge to a measure, not a function. And the other usual defects of convergence are due to oscillation. So I gave the example of oscillation, which was in fact the example we saw in the example before. And with oscillation, as n tends to infinity, un, which is R, converges to 0 weakly, but un squared converges weakly to 1/2 of the cutoff function squared. So there are something fortunate. In fact, in the meantime that Burnett made this conjecture, there has been some mathematical work about the effects of convergence, and There have been, for instance, some work by Patrick Gerard, where he studied intensively what could happen. So if you consider his theorem is the following. If you consider a sequence in L2, which converges weakly to 0, then you can extract a subsequence such that there exists a Radon measure, d mu, on the cotangent sphere, so the set of xp in Rd time Rd, where p is in the tangent space at x of norm 1, such that for all pseudo-differential operator A of order 0, with a principal symbol which is compactly supported, we have that A UNK, scalar UNK, converges as NK tends to infinity to the integral over the cotangent sphere of the symbol of A of xc, time d mu, where d mu is the Radon measure, which is called the microlocal defect measure associated to the sequence UN. And moreover, this, we can have information on this microlocal defect measure if we start with a sequence of function which all satisfy the same equation. So if the UN satisfies P of UN equal to 0, where P is some self-adjoint pseudo-differential operator with symbol P, then mu is supported where P is equal to 0, so that you can write P d mu equal to 0. And also, d mu satisfied a transport equation along the bicharacteristics of P. Okay, so this theorem, in fact, seems very nice for us because this could give us the form of the effective energy impulsion tensor, and also maybe by using the fact that we are considering sequences of solution to Einstein vacuum equation, not any function, then we may get the fact with the first property that mu should be supported on the 0 set of P, we could get the fact that the massless, the Vlasov field is massless, and we should also get a transport equation, which would be the transport equation for our density. Okay. I gave an example of just to fix the ideas. If the defect of convergence is due to concentration, then the microlocal defect measure is a tensor of product of a Dirac and the uniform measure. And for oscillation, it's the contrary. It's the tensor product of the uniform measure time a Dirac in frequency. Okay, just an example. So, as I said, this theorem seems nice for us, but it seems very complicated to apply it to the full set of Einstein equations. So it's why we're restricted to UN symmetry, and I will show you right now what it is and why it simplifies the problem. Okay, so in UN symmetry, we consider manifold which are symmetric with respect to one of the coordinates, so dx3. So the metric can take the form up there, where phi here is a function which depends only on the remaining 3 coordinates. So it's a function on R2 time RT. G is a Lorentzian metric on R2 time RT, and A is a one form. And the Einstein vacuum equation for the 3+1 dimensional metric for G are equivalent to a system of equations for phi omega, which is called the twist potential associated to A. I don't describe what it is, but it's a function. And a G is a 2+1 metric. And these equations are here. So, in fact, the first 2 equations are a wave map. So it's a system of wave equation with, on the right-hand side, a null form. And the Ricci tensor of G is given by 2 terms, which has the sum of the 2 scalar fields, phi and omega. So you can wonder what is the simplification. We started with Ricci equals 0. Now we have a more complicated set of equations. But in fact, there is something different with the Einstein equation in 2+1 dimension, which is they can be recast in an elliptic gauge. So Einstein equations are invariant by diffeomorphism. You can choose which preferred set of coordinates to study them. So without loss of generality, you can always write your metric under this form. You can introduce K, the second fundamental form associated to it, which is like a time derivative of Gij. And so we are in 2 plus 1. We have 3 parameters to fix, in some sense. And 2 choices can be taken to assume that Gij is conformal to a metric diffeomorphic to the Euclidean metric. So this is the first one. We can assume that Gij is e to gamma delta Ij. It's like a gauge choice. And we can also assume that K, the second fundamental form, is traceless. So under this hypothesis, our system becomes a system which coupled the 2 wave equations, which have not changed, and an elliptic equation for G, with on the right-hand side term which are dphi plus term which are gradient G times gradient G. I did not here precise what are the terms which appear, the term in gradient G squared, but in fact it will be important after. So now I can say what is our theorem. So if you consider a solution of Einstein vacuum equation with U1 symmetry that I denote by Gn, phi n, omega n, and which can be written in elliptic gauge, such that there exists some H0, which is this, such that which is also which is smooth. It is something important, and also which can be written in elliptic gauge, such that Hn converges to H0 uniformly, and such that the derivative of Hn converges weakly to derivative of H0 in some LP space, which is specific. Then we can prove that the energy impulsion tensor, the effective one, is a massless, as the form of a massless Vlasov field. But with only this hypothesis, we cannot prove we are not able to prove at least, the transport equation for the density. For this, we need more assumption on how, on the rate of convergence of Hn to H. And with this additional assumption, then the Einstein-Vlasov equations are really satisfied in the sense of measures. Okay. So I will give you some elements of proof just so that you understand a little what is happening. So in fact, what we do is we apply the Gerard theorem that we saw before. We apply it to the derivative of phi and omega. So with this, we prove that there are some random measures, d nu phi and d nu omega, such that derivative of phi n times scalar alpha a, derivative of phi n, where a is a zero-order pseudo-differential operator, converge to this, the integral of a of xc, where a is the symbol of the pseudo-differential operator a, times xc alpha xc beta over xc squared d nu phi. So this is, with this, in fact, you see more of the Vlasov field appearing than before. It's just because we apply it, instead of applying Gerard theorem to the function, we apply it to the derivative of the function. It's where y is xc alpha xc beta appear. So you can, in the same way, define the radon measure d nu omega. And then now we want to pass to the weak limit in our system of equation, which is here. The system of equation, I dropped the subscript lambda, but you should imagine they are there. So, in fact, the term, in the box term, they pass to the weak limit. The semi-linear term, they pass to the weak limit because they are the specific form because they are null forms. So I write it just to simplify in Minkowski. If you have a null form in Minkowski, which is dt phi squared minus gradient of phi squared, you can write it as a divergence. And the divergence, it passes to the weak limit, because if phi converges strongly and dt phi is bounded, then phi dt phi converges to phi 0 dt phi 0, and so the derivative converges in the sense of distribution. So we are happy when we have put our term in divergence form. And the term phi box phi is also nice because box phi is something which is bounded by hypothesis. So this term passes well to the weak limit. And in the equation for G, so the Laplacian of G, in fact, is a true Laplacian, so it passes to the weak limit very easily. The term d phi squared plus d omega squared, they produce the effect of convergence. The defect of convergence they produce can be given in terms of the microlocal defect measure d nu phi and d nu omega, and they are exactly the one we wanted to have. And the term gradient G times gradient G could cause trouble, but in fact, they, in Einstein, in elliptic gauge, they have a very nice form. These terms are, in fact, can be written h squared, where h is a traceless part of the second fundamental form. And in Einstein equation, there is an elliptic equation for h, which says that divergence of h is like d phi squared. And there is also an equation for dth, which says also the same thing, that dth is like d phi squared, very roughly. And d phi squared is bounded in LP0 over 2. And this P0 we choose before, it's just such that the Sobolev space W1 P0 over 2 embeds compactly in L2, which implies that this term gradient G squared, which in fact H squared, do not lead to new defect of convergence. And so this is for the first part of the theorem. More argument, but say that they are the most important one. And for the transport equation. So it's where we use some sort of trilinear compensated compactness. So it's important to know how we get how Patrick Gerard gets the transport equation for the microlocal defect measure. He considered a symbol which is a commutator, pseudo-differential operator, which is the commutator of A and P in his theorem. And so then, just by definition of the microlocal defect measure, this term, commutator of A and P times un, scalar un, converges to the integral of 1 over I times the Poisson bracket of A and P d mu. And on the other side, you can compute what it is, this commutator, and this is AP un plus AUN P adjoint of P times un. And in the case where PUN equal to 0 and P is self-adjoint, in fact, this is 0. And so you obtain that this integral term above is 0. And this is the weak formulation of the transport equation for d mu. And so in our case, of course, we have equation for phi and omega, but these are quasi-linear equations with a metric with dependent phi, and they are semi-linear terms. So, in fact, we have to study trilinear term. So we have to study, we have to replace PUN, for instance, by the null form, dTun minus gradient un squared, and multiply it by dTun because we are considering dt phi because we are considering a derivative and not the function, and study the weak limit of trilinear term of this form. And this is where the compensated compactness appears, because in fact we can express the null form in terms of D'Alembertian of phi squared plus phi times D'Alembertian of phi, and so we can make integration by part and use the fact that phi, or the one we multiply our null form by, satisfies also a wave equation to say that in fact these trilinear terms are of size lambda and converges to 0. Okay, and so we have also to find a similar argument for the interaction with the metric, but that I don't describe here. Okay, and thank you for your attention.
Yeah, thank you very much for your talk. Are there questions from the audience, please?
The reason to study or to consider the U1 symmetry, I mean, one reason is probably that it simplifies. Is there some conceptual reason why to use U1 symmetry?
No, it's just for simplification, because we don't want the problem to be too much simplified. We don't want to just study the example I gave at the beginning, but the full problem is too complicated, so just simplification. And also, in this, with U1 symmetry, we were able to construct very broad class of examples, so we can compare our hypothesis in the theorem with the construction we've made.
More questions? So have you thought about the reverse problem, whether any solution of Lovelock can arise as a limit?
Oh, okay, I did not mention that, but so we started with the reverse problem. We started with, but we were not able to do the full Vlasov case, but a sum of an arbitrary number of null dust.
Okay. And are there questions from the online audience?
No.
Okay, please.
Okay, thank you for a great talk. I have a very elementary question, I think. In the regime of very fast oscillations, as you showed us at the very beginning, there was this limit of cosine with a very high frequency going to infinity. And I might have misunderstood, but it converged to cosine squared or something like that. Could you elaborate on that?
Cosine of so it's the example of the effect of convergence due to oscillation. If you have a cosine of nx0, so you take the squared, it will give you 1/2 plus cosine of 2nx0. And the thing is that the cosine of the cosine of something which is oscillating very fast converges weakly to 0.
Okay, thank you.
Okay, any other questions or comments? Okay, then let's thank Cécile again. And okay, our final talk of the day will again be an online talk, and I'm happy to introduce Harvey Reall from the University of Cambridge. Harvey completed his PhD in 2000 at the University of Cambridge under the supervision of Stephen Hawking, and afterwards he held postdoctoral positions in London and Santa Barbara in California, as well as a lectureship in Nottingham before moving finally to the faculty at Dampt in Cambridge in 2007. The title of his talk today is Well-Posed Formulation of Scalar-Tensor Effective Field Theory. Harvey, please.
Okay. So I hope everyone can see my screen. So thank you very much for the invitation to speak here today. So I'm going to be talking about work that I've done recently in collaboration with Aaron Kovac, which appeared in this pair of papers here. And towards the end of my talk, I'll say something about work that appeared more recently in this paper. So let's start with some motivation. And the motivation comes from gravitational wave detections. So now we can routinely detect gravitational waves from black hole and neutron star mergers. We would like to use those observations to perform precision tests of general relativity in the highly dynamical strong field regime. So in order to do that, because we have to dig the signal out of the data to some extent, we need theoretical predictions for what a deviation from general relativity in this regime would look like. So we need theoretical predictions concerning gravitational waves, for example, from black hole mergers in theories which are not GR, theories which modify GR in some way. Now, it turns out it's rather hard to construct theories or models that predict deviations from GR in vacuum, in other words, for black hole mergers, which is what I'll be focused on. And so a lot of work in this field has made progress by introducing an extra field, namely a scalar field. So that's the class of models I'm going to be discussing. So in more detail, all of the models that people have been focusing on in the numerical relativity and gravitational waves community, they tend to fall into this kind of form. So here's an action for gravity coupled to a scalar field phi. It looks fairly complicated. Let me explain it. This is just the usual Einstein-Hilbert term. X here is just the kinetic term, the conventional kinetic term for a scalar field. And we're allowing for an arbitrary potential for our scalar field. So this is just a conventional scalar-tensor theory. But then we're going to add these extra terms here, which are terms, this term here you can see is quadratic in X, so it's quadratic in the kinetic term for the scalar field, with some coefficient alpha, which depends on the field. And this term here is quadratic in curvature. You may recognize this as the Gauss-Bonnet invariant, sorry, the Euler density associated with the Gauss-Bonnet invariant, which in 4 dimensions is topological, but now we're multiplying it by this function of phi, which means it's no longer topological. Okay, so this is a rather complicated looking theory. So why are we looking at it? Well, the main motivation is that if we were just to consider Einstein gravity minimally coupled to a scalar field, then in a black hole solution, the scalar field would just disperse. And so there wouldn't be any scalar field present in the black hole binary, and therefore it wouldn't affect the gravitational waves, and we would not see any deviation from GR. So the nice thing about this theory is if we now include this coupling, then this term here means that curvature is going to act as a source in the scalar field equation of motion. And that means that the scalar field will be non-trivial even around a black hole solution. So we're guaranteed to see a deviation from general relativity in this theory because of this, this coupling. So that's one reason why this has attracted quite a lot of attention in the community, is because it's guaranteed to deviate from GR. There's also motivation for this coming from effective field theory. So in effective field theory, if we were to write down a theory of gravity coupled to a scalar field, we'd start off by writing down these terms. These are terms which involve up to 2 derivatives of the field, so 2 derivatives of the metric or 2 derivatives of the scalar field. And then in effective field theory, we add that by correcting it with terms involving higher derivatives. These terms involve 4 derivatives of the scalar field or of the metric. And in effective field theory, there's freedom to redefine the fields. So one can use that to try and simplify the form of the theory. And what one can show is that this theory is in fact the most general theory, including 4 derivative terms, with parity symmetry, after you exploit this freedom to perform field redefinition. So in other words, any theory with up to 4 derivative terms can be simplified to this form using the freedom to perform field redefinitions. Furthermore, in effective field theory, you would expect there to be higher terms involving more than 4 derivatives of the field. We're neglecting those. That's only going to be consistent, provided higher derivative terms are small compared to the terms we're retaining, which in turn means that these 4 derivative terms are going to have to be small compared to these 2 derivative terms. So we're always going to be studying this theory in the context that these terms here should be seen as small corrections to the conventional two-derivative Einstein scalar terms. So we refer to this as the weak coupling regime, where we're correcting a conventional two-derivative theory with these four-derivative terms. So here's the theory again. So the final nice thing about this theory, and the reason we're discussing it today, is that even though these terms involve four derivatives of the fields, so you can see this is quadratic in curvature, so it's four derivatives in total. Nevertheless, if you look at the equations of motion do not involve higher than second derivatives. And so this theory then has some hope of making sense classically, in the sense that it might admit a well-posed initial value problem. And of course, if we want to study black hole mergers in this theory, then a well-posed initial value problem would be essential. Now, one comment on that is that from previous work with a student, we know in fact that this theory, well-posedness of the initial value problem can fail if these correction terms become large. So you can see that, for example, by looking at cosmological solutions. If you look at an FLRW solution of this theory and study linear fluctuations around it, then the linear fluctuations governing tensor modes or gravitational waves, their equations can actually change character from hyperbolic to elliptic if the curvature of the FLRW solution becomes sufficiently large. And so this weak coupling assumption, in other words, that these terms are small compared to these terms, is essential not just for consistency of effective field theory, but also is going to be essential for well-posedness of the initial value problem. So we're always going to be making this weak coupling assumption that these terms are small corrections to these terms. Okay, so the question is, does this theory admit a well-posed initial value problem? So let's say a little bit about well-posedness. So a sufficient condition for well-posedness is that the equations of motion are strongly hyperbolic. So this is a technical condition on the equations. I'm not going to go through the details now, but roughly what it means is that there's a certain matrix, which I'll call M, defined in terms of the principal symbol, in other words, the two derivative terms in the equations of motion. This matrix must be diagonalizable with real eigenvalues. So if one has a strongly hyperbolic system, then the initial value problem is well posed. Now, of course, we're not talking about theories of gravity, which possess gauge symmetry. And in gravity, it's well known that to establish well-posedness, we need to find a good gauge and a good way of performing the gauge fixing in the equations of motion. And of course, this is essential for numerics. You have to fix the gauge before you can do any kind of numerical simulation. Now, if we look at a conventional two-derivative theory, in other words, the theory just with gravity minimally coupled to a scalar field, then the simplest choice of gauge in that theory that gives a well-posed or strongly hyperbolic system is harmonic gauge. So in harmonic gauge, this matrix M is diagonalizable and it has real eigenvalues. However, I want to emphasize that the eigenvalues of this matrix are degenerate. And this is associated with the fact that all of the degrees of freedom in this theory propagate at the speed of light. That's essentially what this degeneracy is telling us. Now, the problem with this is that if you have a matrix which is diagonalizable with degenerate eigenvalues, then when you deform it a little bit, you tend to destroy either the diagonalizability or the fact that the eigenvalues are real. So when we look at our scalar-tensor effective field theory, if we view the four derivative terms as a deformation of this matrix M, remember we're treating these as small terms, so this is a small deformation. Because these eigenvalues are degenerate, when we make a small deformation, we tend to ruin this diagonalizability property. So what my student and I showed a few years ago is that in harmonic gauge, when you include these four derivative terms, this matrix develops non-trivial Jordan blocks, even at weak coupling. In other words, even when the fields are small and the four derivative theory you think is close to the two derivative theory. So in harmonic gauge, this theory is not strongly hyperbolic. So harmonic gauge does not work. It does not give a well-posed initial value problem for this, this gravitational theory. I need to say a little bit about where these Jordan blocks come from, and they come from the fact that the harmonic gauge equations of motion admit two types of unphysical solution. So one is that even though the equations are gauge fixed, there's still some residual gauge freedom, and so there are pure gauge solutions of the equations of motion. So these are unphysical because they're pure gauge. And the other type of unphysical solution of the gauge fixed equations is that these equations admit solutions which don't satisfy the gauge condition. So the harmonic gauge Einstein equation admits solutions which don't satisfy the harmonic gauge condition. So that's a second type of unphysical solution. And these Jordan blocks arise from a kind of mixing between these two different types of unphysical solution in harmonic gauge. So the main result of the new work is that we've found a way of fixing this, which is to introduce a new family of what we call modified harmonic gauges for general relativity, and a new way of doing the gauge fixing, which gives a new formulation of the equations of motion for these theories that admits a well-posed initial value problem at weak coupling. So it solves the problem that we set out to solve. So let me explain what these new gauges are. And I'm going to explain this just for conventional GR, so just the standard vacuum Einstein equation, and then we'll turn to the effective field theory in a few minutes. So just in conventional GR, let's now, in our construction, what we have to do is we introduce two additional unphysical Lorentzian metrics. So we call these unphysical metrics G tilde and G hat. And so one of these metrics is used to modify the harmonic gauge condition. So if we ignore the tildes in this equation for the moment, then this would just be the standard harmonic gauge condition of general relativity. So wave operator on the coordinates is 0, or equivalently the contraction of the Christoffel symbols is 0. So if this G tilde was a G hat, this would just be the standard harmonic gauge condition of GR. And all we do is we modify that by replacing G by G tilde here or here. So we've modified the gauge condition by saying that the trace of the Christoffel symbols with respect to G tilde should be 0. This Christoffel symbol, of course, still depends on the metric, the physical metric G. So this involves a mixture of G and G tilde. So that's our modified harmonic gauge condition. The second thing we do is we modify the way that we gauge fix the equation of motion. So here's the vacuum Einstein equation. And the conventional way of gauge fixing this equation in harmonic gauge is to add a term that looks like this. So we have a derivative of this, this h, contracted with this tensor I've called p. So again, so p is defined here. So if this g hat were just a g, then this would just be conventional harmonic gauge written in trace reversed form. Okay, so if g hat was g, this is just harmonic gauge. And the modification we're making is to replace G with G hat, just in this expression for P hat. Okay, so that's how we modify the gauge fixing. What that means is that if we take a divergence of this equation, then this gives 0 from the contracted Bianchi identity, and the divergence reduces to a wave equation for H, the gauge condition functions, where the principal symbol of this equation for H is actually this metric G hat. Okay. So basically what we've achieved here is we've managed to find a formulation where if we look at if we look at pure gauge solutions, or if we look at linearized theory, for example, and we look at linearized gauge transformations and ask when do they satisfy this gauge condition, it turns out they satisfy this gauge condition when the vector generating the gauge transformation satisfies a wave equation with respect to this metric G tilde, okay, which you can sort of see from here. Okay, so pure gauge solutions in this approach propagate along the null cone of G tilde. And from what I just told you here, the gauge condition violating solutions, in other words, solutions with H non-zero, propagate along the null cone of G hat, the other unphysical metric. And I should emphasize G tilde and G hat are completely unphysical. We just introduce them to fix the gauge. The physical solutions of this equation are exactly the same as the physical solutions in any other gauge, which are these physical solutions propagate along the null cone of the physical metric G. Okay, so that's our gauge, that's our definition of modified harmonic gauge, and you can see it depends just on the choice of these two metrics, G tilde and G hat. So I need to tell you how we choose these two metrics. And essentially the only important thing we need to arrange is that the null cones of these unphysical metrics do not intersect each other, or the null cone of the physical metric. So in the cotangent space, this is what we do. So here in purple is the null cone of the physical metric. In orange and green are then the null cones of the two unphysical metrics. And you can see we've arranged them so that they form this nested set, as I show on the left here. This is in the cotangent space. If we invert these metrics, we can look at the cones in the tangent space. These are also nested, but the nesting is now in the opposite direction. So the way I've chosen the nesting here means that the physical metric has the outermost cone, and then the two unphysical metrics have these inner cones. So this means that the physical degrees of freedom in this formulation are the fastest propagating degrees of freedom. So with this choice of gauge, we can prove that just conventional GR, the vacuum Einstein equation, is indeed strongly hyperbolic, and therefore we have a well-posed initial value problem for just conventional GR. We then want to include a scalar field. It's straightforward to include a minimally coupled scalar field. In other words, this two-derivative theory that I was discussing earlier. So far, this is all just a different choice of gauge for things where we already had a good choice of gauge. But now we want to go on to include these four derivative terms in our effective field theory. Okay. So remember the failure of well-posedness of this theory in conventional harmonic gauge was associated with this mixing between these unphysical solutions, between pure gauge and gauge condition violating solutions. And this mixing occurs in harmonic gauge when we make this deformation. The beauty of this modified harmonic gauge is that we've now arranged that these two different types of unphysical modes propagate along different null cones. They propagate with different speeds. And this prevents the mixing from occurring when you deform the theory to include these four derivative terms. So we can then use a continuity argument to prove that the equations of this scalar-tensor effective field theory remain strongly hyperbolic when we include these four derivative terms at weak coupling. So we've solved the problem that we set out to solve. We found a well-posed formulation of the equations. Okay, so the formulation, of course, depends on these two auxiliary metrics, G tilde and G hat. So I need to tell you how we choose these two metrics. There are infinitely many ways of doing it, but one possibility is what I've shown here. So let's imagine we're doing a numerical simulation. We have some foliation by constant time slices, and we then choose G tilde to be related to the physical metric like this. So n here is the unit normal to our constant time slices. We just subtract a constant multiple of n mu n nu from G, that defines G tilde or G hat. And so if you choose these constants A and B appropriately, you'll get null cones nested in the desired way. Okay, so this is all formalism. Does it actually work? Well, it should work because we argued that we showed that it's strongly hyperbolic, so it should be well posed. And indeed, the first numerical simulations have now been performed using this approach by East and Ripley, who've considered a particular example of a so-called shift symmetric theory. So this is a particular example theory of the type I'm discussing. We have gravity minimally coupled to a scalar field, and then with this curvature coupling. This is called shift symmetric because the equations of motion are invariant under constant shifts in the field phi. Now, so they studied various things in this theory. So for example, one thing they looked at is you can start out with initial data in which the scalar field is trivial, is absent. So for example, you could start out with initial data describing a Kerr black hole in this theory. But because of this coupling, when you evolve this data, the scalar field will become non-trivial, and you'll settle down to a new black hole solution which has non-trivial scalar field. They studied also, more importantly, they studied in-spiral and merger of black holes in this theory, and made a first attempt at looking at the gravitational waves produced in such a merger. So I should emphasize, as I've done several times, that all of this only makes sense when these high derivative terms are small compared to the two derivative terms. So a dimensionless quantity which measures that smallness is this coupling lambda times the curvature, for example, at the horizon of a black hole, which goes like 1 over m squared, where m is the mass of the black hole. And this dimensionless combination in their simulations ranged from 0.01 to about 0.2. So this, of course, is very small. This is getting a bit bigger. If you made this much bigger than this, at some point we're going to expect to encounter the problems where well-posedness fails if we make this too big. Okay, so let me say something about generalizations of this. So I've told you about these scalar-tensor effective field theories. These are actually part of a larger class of theories called Horndeski theories. So Horndeski theories are the most general scalar-tensor theories with second-order equations of motion. And our formulation works for all of those theories, again, subject to this weak coupling assumption. And it also works for so-called Lovelock theories. So Lovelock theories are theories of vacuum gravity in higher dimensions. These are theories, again, with second-order equations of motion, just involving the metric. So the simplest example of a Lovelock theory is called Einstein-Gauss-Bonnet, and it has an action which looks like this. So we have Einstein-Hilbert plus the Gauss-Bonnet term. So this term would be topological in 4 dimensions, but it's not topological in higher dimensions, and it gives you a non-trivial contribution to the equations of motion. And in fact, using field redefinitions, you can argue that this is the most general 4-derivative effective field theory correction to conventional Einstein theory. So our formalism works for this at weak coupling. So this might be interesting. You could use this, for example, to study the effects of these higher curvature corrections numerically in dynamical processes in higher dimensional gravity. So an interesting one to look at might be the black string instability of Gregory and Laflamme. Okay, let me now switch direction for the last few minutes and tell you about the more recent work. So if we look at just conventional 2-derivative Einstein or Einstein scalar field equation, then the physical characteristics psi are of course null with respect to the metric. So the physical characteristics are null. Now in our effective field theory, our weakly coupled effective field theory, this is no longer true. So in this theory, the physical characteristics will lie on a cone which is close to the null cone of the metric, but it doesn't coincide with it. It's close because of this weak coupling assumption. So the question is, can we understand the properties of this characteristic cone in an arbitrary, weakly coupled background solution of this theory? And so I did this using if you're focusing on the physical characteristics, there's a nice way of doing this, which is independent of any kind of gauge fixing procedure, which I learnt about in some lectures of Christodoulou. So using this approach, one can look at, discuss physical characteristics for any diffeomorphism invariant theory of gravity with second order equations of motion. And in particular, if you look at these scalar-tensor effective field theories, or indeed any Horndeski theory, then this leads to a fairly explicit characterization of the characteristics in an arbitrary background, which is what we wanted to achieve. So the result is the following. So it turns out that in these theories that psi is characteristic if and only if it satisfies a certain polynomial equation. P here is a homogeneous polynomial of degree 6, whose coefficients depend on the background fields, the metric and the scalar field, and their first and second derivatives. Okay. Notice degree 6, well, notice this system has 3 degrees of freedom. It has 2 metric and 1 scalar field degree of freedom. And with 3 degrees of freedom, degree 6 is the minimum possible you would expect for the characteristic polynomial. And that's exactly what we have. What's remarkable is that this degree 6 polynomial actually factorizes into a product of quadratic and quartic polynomials. This is actually analogous to what happens in elasticity theory. If you look at an anisotropic elastic solid, such as zinc, with hexagonal symmetry, then that also has a characteristic polynomial of degree 6, which factorizes in the same way. So in some ways in these theories, the universe is a bit like zinc. So, of course, if you look at special cases like the 2-derivative theory, you get further factorization. So this quartic factorizes back down, and this degree 6 polynomial just reduces to the cube of the norm of psi with respect to the metric. In other words, you just recover the fact that the characteristics are null. But this is just for the 2-derivative theory. In the 4-derivative theory, generally, this is quartic polynomial is quite complicated. You can find other cases where you get this factorization of the quartics. So, for example, if you look at symmetrical backgrounds, such as FLRW, then you will also get some further factorization. So what you can show then is that the characteristic cone, P of psi is equal to 0, at weak coupling has 3 sheets corresponding to the 3 degrees of freedom, and it's the union of a quadratic cone and a quartic cone. So just to end, let me say something about black holes in these theories. So the characteristic cone is defined in the cotangent space. To discuss causality, we need to look at the dual cone defined in the tangent space, which should then be used to define basic notions of causality in these theories. So using this dual cone, you can define what you mean by a black hole in this theory in the usual way, so that the event horizon of a black hole would be a characteristic surface in the sense I've been discussing. So I think it would be interesting to study the properties of black holes according to this definition in more detail. So I made a start on this in my paper by looking at solutions with a killing horizon. So we assume we have a killing horizon, and we assume that the scalar field is invariant under that killing symmetry. What I could show then is that if you have a killing horizon, then it's characteristic for all 3 degrees of freedom. That's interesting because in these theories, you can have superluminality. At weak coupling, you can have things propagating slightly faster than light. So you might think it would be possible to escape from a killing horizon. But because the killing horizon is characteristic for all of the degrees of freedom, that's actually false. You can't escape from behind the killing horizon. And so it's evidence that the killing horizon would actually be a black hole horizon. Secondly, you can prove that the 0th law of black hole mechanics, the constancy of the surface gravity, also holds in this theory. I should emphasize that this weak coupling assumption that the high derivative corrections are small compared to the 2 derivative terms is essential for proving these results. So in summary, I've introduced a new class of modified harmonic gauges for general relativity, and we've shown that they lead to well-posedness of the initial value problem for these scalar-tensor effective field theories subject to this crucial weak coupling assumption. I've told you the first simulations of black hole mergers have been performed using this formulation. And I've told you about a method for determining the physical characteristics of any gravitational theory with second-order equations of motion, which, when you apply it to the scalar-tensor effective field theories, gives you an explicit form for the characteristic polynomial of degree 6, which surprisingly always factorizes into a quartic times a quadratic. So in future, we're going to be looking at extending these results on the scalar-tensor effective field theory to other effective field theories, such as Einstein-Maxwell effective field theory, where we consider 4 derivative corrections to the conventional Einstein-Maxwell theory. Okay, so that's the end of my presentation. Thank you for listening.
Yeah, thank you very much for your talk. Questions or comments from the audience? Please.
Thanks very much for the talk. Just a simple question regarding the numerics you mentioned. Is there any feedback in that regard?
Is there any what, sorry?
Regarding the numerics, you said that they have been performed using your framework. How does it compare to the actual Einstein equations?
Oh, okay. So it depends, of course, on the size of this coupling. So I should say the way I think about this is that I don't expect to see any deviation from GR, but we want some way of parameterizing how well we've tested GR. So one way of parameterizing it would be to place bounds on this coefficient lambda here, for example. So the smaller you've constrained lambda to be, the better you've tested GR. Okay, so if you make lambda very small, then you'll get results which are very similar to GR. But as you increase lambda, you start to deviate more and more from GR. Okay, so I think the current constraints on lambda are kind of around the kilometer scale, which is what you'd crudely expect. But once people start to perform simulations in these theories more systematically, which they can do now, then it should be possible to improve the bounds on lambda by comparing with observations.
Maybe a follow-up on this. Can they measure in the experiment with so much resolution that they can actually distinguish the new predictions from the old, sort of? Because you're comparing with the original templates, presumably, that usual GR.
Yes. So all, I mean, at the moment, everything we see is consistent with GR, right? So all we can do is place bounds on lambda. At some point, maybe the observations will see something which can't be explained using conventional GR, but can be explained using this kind of approach. But I think I should say, what one wants to do is to develop templates for binary black hole mergers in theories of this type. So one can add them to the template banks, which are used when one matches to the signal, and then try and place bounds on lambda from those observations. There might be degeneracy, for example, between theories of this type and just varying the parameters of the orbit in GR. So you need to be careful about this. But it's early days yet. At the moment, all they've done is one very simple study of in-spiral and merger in these theories. But to do this, really carry out this program of testing GR in the strong field regime using this kind of approach, you need to now go on to develop template banks of results from black hole mergers to compare with observations.
Well, thank you. Any other questions? Yes, please.
Just in your initial Lagrangian, you had a potential and scalar fields which had higher derivatives. And now that could admit soliton solutions, skyrmion type things, if your potential has multiple vacua. Did you consider that at all?
No, I mean, people obviously have considered that. I mean, if you choose your potential appropriately, as you say, you could have different kinds of solitons and so on. But I mean, I just included this potential for completeness. Really, it's not playing a role in anything I'm discussing because it doesn't affect the issue of well-posedness, which is the issue I'm focused on. I mean, if you just look at this theory here, that's just conventional Einstein scalar theory. That's well known to be well-posed. The point was that people have been focused in particular on this interaction here for the reasons I explained. And because this is a higher derivative interaction, the issue of well-posedness is very far from clear. And for a long time, there was a lot of discussion about how one would obtain a well-posed formulation of the equations of motion, or indeed, could it be that no well-posed formulation exists? That might have been the case, but it turns out, because of our work, that the theory does admit a well-posed initial value problem, as I've explained.
Are there questions from the online audience?
No.
Okay, and last chance to ask some questions from this audience. Yes, please.
Maybe you had this gauge condition with the two different G's. you introduced, are there like different choices of this G tilde and G bar that give interesting, that lead to the interesting aspects, or is there like one sensible choice?
No, there's a lot of freedom in how you choose them. I mean, for the well-posedness, really all that matters is that the null cones are nested in the way that I described. But one thing I should emphasize is that this modified harmonic gauge formulation, as I explained, you could do it in conventional GR. You don't have to look at exotic scalar-tensor theories. And so one thing we did speculate about is that this formulation might have advantages even for conventional GR. So there's a particular class of gauges that people in numerical relativity like to work on. And it's called the 1+ log slicing, I think. And so the freedom to choose these metrics seemed to give a fairly nice way of implementing that condition. So that formulation, that slicing condition is nice for singularity avoidance properties. So it might be that the freedom to adjust these metrics would be advantageous just in conventional numerical relativity in GR for trying to ensure that your simulation lasts for longer before it runs into some problem with a singularity or so on. So at the moment, that's certainly something that might be true and that we're thinking a little bit about.
Thank you.
Okay, then I think it's a good opportunity to thank Javi again for his talk, and Javi, also for you, a medal that we'll send to you to commemorate the occasion. Thank you very much. And yeah, and perhaps we can thank all speakers again for their talks. Thank you for coming and delivering your talks. And yeah, maybe we do that first. And then I wanted to remind you of the talk in the morning of Jeremy Sheftel, and also there's another session on Friday evening at 6 p.m. on general relativity. So hope to see many of you there.